Hello, myself Professor H.K. Bangare from Department of Electrical Engineering, SND College of Engineering and Research Center, Evla. So today we are discussing basic electrical engineering of first year engineering course. We are discussing alternating current part 6. We have already discussed the fundamentals of AC. In that we discussed what is crest factor, what is peak factor, RMS value, average value, how to find analytically and graphically all these values. Also, what is power factor, so that we have already discussed. Now in part 6, we'll discuss about the phase representation, vector representation, what is phase shift. Okay, so that we'll discuss now. So here is the vector representation. So in vector representation, this is nothing but a sinusoidal waveform, right? And V1 is the instantaneous value of that sinusoidal waveform. And it's a phase angle that is 0, means its direction. A vector is nothing but what? It has a magnitude and a direction. So the magnitude of this phase, magnitude of this sinusoidal waveform is V1, and its direction is, it is along a positive x-axis, means it is 0 degree. So the angle or the direction is towards the positive x-axis, means it's the angle with the positive x-axis is 0. So that's why this sinusoidal waveform can be represented in the form of this vector having its magnitude and its direction. So here the different three waveforms are shown. All have a 0 phase difference, phase angle. Now the magnitude of these three waveforms is different. This magnitude of the first waveform is less than that of magnitude of second waveform. Magnitude of second waveform is again less than that of magnitude of third waveform, and the corresponding vector representation of this waveform is shown here. So this is the vector representation of the first waveform, its direction. All the waveforms have the same direction, and their direction is along a x-axis, means they are making 0 degree with the x-axis. That's why 0 angle, phase angle is 0 degree, and its length indicates the magnitude or the amplitude of that waveform. So for first vector represented, its length or the amplitude or the magnitude is less than that of the second vector and that of the third vector. So in this way, these different three waveforms can be represented in the form of the vector representation. It shows its amplitude as well as its direction. Now here is the phase shift. Now the vector representation is nothing but it is a phasor representation. The phasor, what it represents, the magnitude or the amplitude of the waveform and its direction. So here the two different waveforms are shown, waveform A and waveform B. Now waveform A and waveform B, we can say that they have a certain magnitude, and the magnitude is the same here, but the phase angle of both the waveform is different. So here I can say that the waveform A appears first than that of the waveform B, means I can say that A is ahead of that of B, means in other words I can say that the A leads B. In other words, I can say that the leading waveform is one whose 0 value and its maximum value appears first. So the 0 and maximum value of waveform A appears first than that of waveform B. That's why A leads B. Now in second diagram, here the waveforms are again shown. First is B waveform, second one is A waveform. Now here again the phase shift between both the waveform is 90 degree. Now we can say that B is ahead of A. So B leads A, means the 0 value and the maximum value of B waveform appears first, comes first. That's why B waveform leads A. And there is 90 degree of phase shift in between B and A. Now in third figure, if you observe, waveform A is this one and waveform B is this one. Now if you observe, so it is exactly opposite to each other. So the phase difference or the phase shift between the both the waveform is 90 degree. The phase shift between the both the waveform is 90 degree, means A and B waveforms are mirror images of each other, and we can say that they are in phase opposition. We can say that this waveform A and B are in phase opposition, and whenever the phase shift is of 180 degree, that time they are in phase opposition. Now fourth figure, if you observe, waveform A and B both are coincide with each other. So the phase shift in between A and B is 0 degree. So A and B waveforms are in perfect state with each other. That's why the phase angle or the phase angle of both the waveform is 0 degree, and phase shift between them is again 0 degree. No difference in the phase angle. That's why they are coinciding with each other, and A and B, they are, we can say that they are in phase with each other. Now again the phase shift representation here, A and B are shown, the phase relationship is shown, and vector representation of that waveform is shown here. So here A and B both are in phase, means phase shift between them is 0 degree. A and B waveforms are in perfect state with each other, and the vector representation means its phasor representation can be represented like this. This is A, and on the same perfect step with that is a B waveform, and the magnitude of both is again same. That's why A and B have same direction and same magnitude, and its vector or the phasor representation can be a simply straight line making an angle of 0 degree with the 0 axis. Now here second diagram, if you observe, waveform A and waveform B are shown. Here a phase difference of 90 degrees is there. A waveform is leading with B waveform. So A is ahead of B. So the phasor representation of A and phasor representation of B are different. So B and A is ahead of B, and it is 90 degree ahead, means it is 90 degree ahead of B. So its phasor is, it make an angle of 90 degree with your baseline, that is with the 0 degree axis, and this is the phasor representation of the A, while this horizontal line along the x-axis, positive x-axis, it is a phasor representation of the B, and this is the angle or phase shift between A and B, that is 90 degree angle. Now third diagram, if you observe, here A and B both waveforms are there. Again this phase shift between them is 90 degree, but here B is ahead of A. B is ahead of A, means I can, in other words, can say that A is lagging behind than B. So A is lagging behind by 90 degrees, means a phase difference of 90 degrees is there, but A is lagging behind. So B's phasor representation is a straight line along a 0 degree axis, while A phasor diagram is in a minus 90 degree, means it minus negative y-axis. So it is the representation of the A vector or A waveform's phasor diagram. It is the phasor for the B waveform, and the phase difference between them is 90 degree, and A is lagging behind B, that's why it is minus 90 degree. Now last waveform A and B are in phase opposition, means phase difference between them is 180 degree. So they are the mirror images of each other, and that time the direction of both, though magnitude is same, direction is opposite. So B is along the positive x-axis and A is along the negative axis. A is on 0 degree axis and B is on 180 degree axis. So that is nothing but the phasor representation or the vector representation of the waveform A and B. The phase shift between them is 180 degree. Then here A and B, the phase shift is there. Let us say this certain phase shift of angle alpha is there. So that can be shown that B is 0 degree making with angle and A is ahead of that making an angle of alpha, whatever the angle may be. So the phase representation can be shown like this. A is represented like this. So it is the phasor representation. Now next is the DC quantity representation. How the DC quantity is represented? So suppose a battery is there, 6-volt battery is there, 8-volt battery is there. Okay, so their total they are connected in series, minus plus minus plus. So total voltage across these two terminal is 8 plus 6, that is 14 volt. So here we will get the 14 volt. So we can represent the DC quantity with the symbol of a battery, and its magnitude is 6 volt, their magnitude is 8 volt, and both are connected in series, and hence the magnitude can be added. So like this, that is it is 6 volt plus 8 volt, and it is 14 volt you will get. So the simple vector addition. So how the vector addition will take place, just like the battery's magnitude is added. Now here the 0 degree 6 volt, and direction is, it is along the 0 degree axis. It is 8 volt along the 0 degree axis, and here it is a vector quantity, means it is AC quantity. This is also AC quantity. So AC quantity always have a magnitude as well as direction, while DC quantity it has only magnitude. So here 8 volt 0 degree, 6 volt 0 degree, they are connected in series. So here the resultant, the addition of both the vectors, vector addition can be done just like a 6 plus 8 volt, means this is vector representation of 6 volt 0 degree angle, length 8, another vector representation. Okay, its length is more, 2 units are more, and direction is same. That's why they are added. So vector addition takes place, and the resultant vector is 14, 6 plus 8, 14 volt, and angle is 0 degree. So the vector magnitudes add like a scalar for a common angle. If the angle is common, then they are added just like a scalar quantity. Now here length is 6. This is a vector having a length 6 and direction is towards 0 degree. Angle is 0 degree. Another vector having magnitude 8 and its angle is 180 degree. Means both are opposite in direction. It is along 0 degree axis. It is on a 180 degree axis. Both are in opposite. Means the total length or the resultant magnitude of both is, total length is equal to 6 minus 8 is equal to minus 2 at 0 degree axis, and 8 minus 6 is equal to plus 2 at 180 degree axis. So in this way, the resultant can be denoted or the phasor can be represented. So this is all about the phasor or the vector representation of the AC quantities. So thank you. Next time we will discuss with the next topic. Till then, goodbye.